All right, everyone. Welcome to the next class for the AMC10 Basic. Anyways, so please do the fun problem of the day while we wait for more people to come in. Okay, so I'll start going over this now. So first of all, this expression can easily be factored. So n cubed minus n equals n times n squared minus 1 equals n times n minus 1 times n plus 1. All right. And so there's more than two consecutive numbers in here. And when you have more than two or more consecutive numbers, then at least one of them must be a multiple of 2. Because if the smaller one is already even, then you're already done. And if the smaller one is odd, then the other one, because the number larger than it, must be even. And you can apply almost the same logic for 3 consecutive numbers. And you know that n minus 1, n, and n plus 1 are also 3 consecutive numbers. So one of these must also be a multiple of 3. And you can show this by assuming that n minus 1 is 0, 1, or 2 mod 3, and showing there's something in all 3 cases that works. And so you know that 6 must divide n cubed minus n. And here I'm just using the shorthand a slash b, or however you want to call it. And this basically just means a divides b. And I might use this more later on. And so you know that 6 must divide n cubed minus n. And now when you plug in n equals 2, you have that n cubed minus n equals 2 cubed minus 2, which is 6. And so that tells you that there are no more larger possible values that can divide n cubed minus n. So the answer is just 6. Are there any questions? All right, so this week is going to be covering number theory. Okay, so this week, to be more precise, we're going to go over integers. What are they exactly? Some divisibility rules, what prime numbers are, Diophantine equations, what are the GCD and LCM, the sum of divisors, and we're also going to cover what bases are. And so, all right, and this week we're not going to go over homework because everyone who submitted it did well. And so we're going to start on integers, and I'm going to assume all of you already know what integers basically are, and we've already gone over what arithmetic sequences are, so we can just start off with a problem. And if you forgot what integers are, they're basically things in a sequence in the form a plus c, a plus 2d, etc., where a is the first term and d is the common difference. These aren't logs. This is just like standard notation for an arithmetic sequence. For example, like AN is the nth term of the arithmetic sequence. It's not any kind of log. We're not going over any AMC12 content yet. Okay, so you can see here that these all have a difference of 100. And so you can see that if you subtract these two equations, you can group the terms. So what you get is A101 minus A1 plus A102 minus A2 plus all the way to plus A200 minus A100. And this just equals 100. And now, you know that the difference between A, you know that A100 plus N minus AN, you know that this should equal a 100D because you can just, and it would be A plus 100 plus N times D minus A minus ND, and that just equals 100D. So all of these combined, it's simply just 100 squared D equals 100. And so you find that D equals 0.01. And now what you want to find, A2 minus A1, is just A1 plus D minus A1 equals D. And so that would equal 0.01. So are there any questions? All right, so let's move on to the second problem. Alright, I'll start going over this now. So the sum of 18 consecutive positive integers is a perfect square. And we want to find the minimum possible value of the sum. And so 18 consecutive numbers, since we're given that they're positive, so using their average as a variable is not always the best idea because it's harder to tell when all numbers are actually positive. So you can set the variable to be the smallest number. So let that be A. And then the 18 numbers would be A plus 1, A plus 2, all the way to A plus 17. And so when you find the sum of all of these, it's just A plus 1 plus all the way to plus A plus 17 plus 2 plus 3 plus all the way to plus 17, which is 18A plus 18 times 17 over 2, or 9 times 2A plus 17. And so this must be a perfect square, so it must equal k squared for some integer k. And now 9 is already a perfect square, so we can effectively ignore it. So what we really want is that 2a plus 17, we want that to be a perfect square. And so a must be positive, so 2a plus 17 is greater than 17, and the smallest perfect square that's greater than 17 is 25. And so if you set 2a plus 17 to equal 25, you get that this result in a equals 4, which means that this sequence does work. And so the smallest possible value of the 18 consecutive positive integers is 9 times 25, which is 225. All right, so are there any questions? All right, so we're going to move on to divisibility rules. So for 2, then the divisibility rule is that the last digit is even, meaning that it's 0, 2, 4, 6, or 8. And the divisibility rule for 3 and 9 is when the sum of the digits is divisible by 3 or 9. And when the last two digits are divisible by 4. And for 5, it's when the last digit is 0 or 5. And because 6 is just 2 times 3, so you can apply the rules for just 2 and 3 to prove if an integer is a multiple of 6. And now 7. So you have to double the last digit and then subtract it from the number that you result in when you remove the last digit from the number. And if the result is divisible by 7, then the original number was divisible by 7. So an example would be 672. And in here, the last digit is 2, and the other number digits left behind are 67. So you really want to see if 67 minus 2 times 2 is a multiple of 7, and this equals 63, which is 7 times 9. So 672 is a multiple of 7. And for 8, the last 3 digits are divisible by 8, would imply that the original number is divisible by 8. And 10 is when the last digit of the number is 0. And the divisibility rule for 11 is when the alternating sum of the digits is divisible by 11. And with the rightmost digit being the subtracted number. And for the cases of 3, 9, and 11, the resulting number is simply the remainder when the number is divisible divided by the original number. For example, the sum of the digits of 73 is 10, which is 1 when you divide it by 9, and the same thing is true for 73. What was that? Okay. All right. So here's your first example for divisibility rules. Okay, so I'll start going over this now. Okay, sorry. So you can multiply the. n- Okay, so you want to find the minimum number of digits to the right of the decimal point when this is written as a decimal. And so here by 5 to the power of 22. And this is just so you can make the denominator a simple one simple power. And so that makes the denominator 10 to the 26, and the numerator becomes 5 to the 22 times 1, 2, 3, 4, 5, 6, 7, 8, 9. And so now you want to find the number of digits to the right of the decimal point of 5 to the 22 times 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by 10 to the 26. And now we know that every time you divide by 10, every time you divide a number by 10, all you're basically doing is moving the decimal point one space to the left. And we know that this currently has 0 digits to the right of the decimal point. So when you divide it by 10, there's 1 digit to the right of the decimal point. When you divide by 10 squared, there's 5 to the 5 to the 22nd equals 2 to the 26th. And okay, so once you get that, it's this number divided by 10 to the 26th. Then whenever you divide a number by 10, you basically just shift the decimal point one space to the left. And so if there okay, this is expressed as a decimal. And so you can simplify this number by, I'll just take this top number to be k because writing that out is a lot shorter. So k over 2 to the 26th times 5 to the 4th equals k times 2 to 5 to the 22nd over 2 to the 26th times 5 to the 26th. And so this is 5 to the 22nd times k over 10 to the 26th. All right. And so whenever you divide a number by 10, so my example number is going to be like 103597246.0. So currently there's 0 digits to the right of the decimal points. And now when you divide this number by 10 once, there is now 1 digit to the right of the decimal point. And when you divide it by 2 tens, there is now 2 digits. That tells you that there's 26 digits to the right of the decimal point. So did that answer your question? All right, so let's move on to prime numbers and prime factorization. And so just a quick review, a prime number is basically a number that's, and their only positive factors are 1 and itself. And the prime factorization number is the unique factorization of a number into the product of powers of multiple primes. So like the prime factorization of 12 equals 2 squared times 3, 13 is just 13, 14 is 2 times 7. And that's basically what a prime factorization is. All right, so now you can try to do this problem. Alright, so I'll start going over this problem. So we want to find for how many positive integers n are there such that this is prime. And so when we see this, we should almost immediately realize that this factors as n minus 2 times n minus 1. And now we can see that these are two consecutive integers. And that means that at least one of them is even. But there are almost no even primes. The only even prime is 2. And since we want it to be a prime number, that means that n minus 2 times n minus 1 must equal 2. And so n squared minus 3n plus 2 must equal 2. And just this means that n squared minus 3n equals 0. And when you solve this, you find that n equals 0 or n equals 3. But you're given that n is positive, which means that 0, it cannot be a possible answer. So the answer must be 3. And since you want how many there are, the answer is 1. And the only one being 3. Are there any questions? All right, so here's the next example. All right, I'll start going over this. So we're using the digits 1, 2, 3, 4, 5, 6, 7, 9 to form four two-digit primes. And so we should be able to easily see that there are four digits here who would result in a number not being prime if it's the units digits, namely being 2, 4, 5, and 6. And it's because we're given that they're two-digit prime numbers. And that means that the number cannot be even and the number can't be a multiple of 5. But if the last digit is 2, 4, or 6, then the number is even. And if the last digit is 5, then the number is a multiple of 5. So these four numbers must actually be the 10th digits. And so there's only four two-digit prime numbers that we're forming, which means that 1, 3, 7, and 9 are the units digits. So the sum of the four prime numbers is 60 plus 50 plus 40 plus 20 plus 9 plus 7 plus 3 plus 1. And this just adds up to 190. And if you want a construction of this, an example would be 23, 41, 59, and 67. And you can verify for yourself that these add to 190. All right, so are there any questions? All right, so Diophantine equations. So a Diophantine equation in the form is a Diophantine equation is basically any equation with solutions over the integers. And so a Diophantine of the form ax plus by equals c is known as a linear combination. If two relatively prime integers a and b are written in this form with c equals 1, the equation will have an infinite number of solutions. And more generally, there will always be an infinite number of solutions if the GCD of a and b is 1. If the GCD of a and b does not divide c, then there are no solutions to the equation. And to see why, there's an example given, which is 3x minus 9y equals 17. And so 3 is the divisor of the left-hand side because 3x minus 9y factors as 3 times x minus 3y. So 3 divides the left-hand side, while the right-hand side, 17, is never a multiple of 3. So there are no solutions. And now, if it's the case that c equals 0, then ax equals negative by. And so this always has solutions. And now, Bezout's lemma is a lemma, and it basically says that if x and y are non-zero integers, and if you let g or d be the GCD of x and y, then there exists integers alpha and beta such that x times alpha plus y times beta equals g. And in other words, this basically says that there exists a linear combination of x and y that equals g. And this holds true for any non-zero integers, x and y. And furthermore, g is the smallest positive integer that can be expressed in this form. And that basically means that all values of ax plus by must divide g. G divides all values of that. And so if x and y are relatively prime, then Bezout basically says that there are integers a and b such that ax plus by equals 1. All right, so here's an example of problem number 1. Alright, so I'll start going over this. So, two farmers agree that pigs are worth 300 and goats are worth 210. And so, let there be P pigs and G goats. And so, when one farmer owes the other money, he pays in pigs and goats with change received. And so, you want to find the amount of the smallest positive debt that can be resolved this way. So, P pigs and G goats. So then money can be expressed in the form 300p plus 210g. And so you want to find this. So what you basically want to find is the minimum value of this, given that it's still larger than 0. So obviously you can't have a fraction of a pig or a goat. So p and g must be integers. And that means that this is of the form 300p plus 210g equals c. And so this is a linear Diophantine equation. And so Bezout's identity tells you that the minimum possible value of C equals the GCD of 300 and 210, which is 30. And to see that 30 is possible, one way is for 3 goats and the change would be 2 pigs. A payment of 3 goats with a change of 2 pigs. And that's 3 times 210 minus 2 times 300 equals 30. Are there any questions? All right, so let's move on to the number and sum of divisors. So, okay, so the number of divisors of an integer n that can be prime factorized into the form p1, e1, p2, e2, all the way to pk, ek. The number of divisors of n would be e1 plus 1, e2 plus 1, e3 plus 1, all the way to ek plus 1. And that's the number of divisors there are. So yeah, you can now try problem number 1. All right, I'll start going over this. So let n, so n has 60 divisors, and 7n has 80 divisors. So the only difference between n and 7n is the power of 7, so we can see that we mostly care about the power of 7. And so we can factor n as 7 to the k times m, where 7 does not divide m. And this notation just means a does not divide b. And so 7n equals 7 to the k plus 1 times m. And so you can see that if you let d of k be the number of divisors of k, then d of n equals d of 7 to the k times m, and this equals k plus 1 times d of m. And now you can do the same for d of 7n. And this equals d of 7 to the k plus 1 times m. And you can do almost the same thing as the equation up here. And so you get this. D of 7n equals k plus 2 times d of n. And so Now you can divide d of m 7n and d of n. So you know that 80 over 60 equals k plus 2 times d of m over k plus 1 d of m. And so this just equals 4/3. So 4k plus 4 equals 3k plus 6. And so k equals 2. And the answer would just be 2, because we want to find the greatest k such that 7 to the k divides n. So are there any questions? All right, so sorry. Let's move on to the final question for today. Um, so I have slightly more planned after this, so I'll just directly give all of you a hint. So, so they're distinct powers of 3. So each of these numbers in base 3 is a sequence of ones and zeros. For example, so the first few terms of this in base 3 are 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, etc. And this should be really familiar. All right. So I'll just start going over this now because it's a pretty hard question. So when you see this sequence, it should remind you of binary. And now the reason this is binary is because you're told that it's sums of distinct powers of 3. And if there's ever a 2 in the base 3 sequence, then it would no longer be distinct powers of 3 because you would need 2 copies of that exact power of 3. And so you can just convert this into binary. So now what you really want is to find 100 in binary. So 100 is 64 plus 32 plus 4. So in binary, that's 11000100 base 2. Yeah, all right. But you want the hundredth term in base 10, and you need to convert this into base, and you need to turn this into base 3. So now you want to convert this into base 10. So the result is just 9 plus 3 to the 5th plus 3 to the 6th equals 9 plus 243 plus 729. And when you do the addition, the answer is 981. So are there any questions? Alright, so the key point of this problem was basically you converted this into base 3 and you saw what basically looks like binary, and you realized it has to be binary due to the fact that the problem specifies sums of distinct powers of 3. So then you convert 100 into binary, take the results, turn the base into base 3, and convert that back to base 10. Yeah. So that was basically the solution outline for this problem. And so happy holidays, everyone, and we're going to have a Kahoot now. Okay, so happy holidays, everyone. And we're probably gonna host another event over the break, and there will be updates about that in the classroom. And I hope all of you have a Merry Christmas. Bye.